Okay, so in this lecture, let us discuss the implementation of linear phase FIR filters. So we know that for a linear phase FIR filter, h of n is equal to h of capital N minus 1 minus n. Okay, so obviously if the finite impulse response filter was was linear phase, then the number of multipliers can be reduced approximately by half, right? If the length is even, length n, capital N is even, then the number of multipliers can be reduced by half. And then if the length capital N is odd, then the number of multipliers that you would require is n plus 1 by 2. And the discipline that we follow to draw the structure is as follows. If length equal to capital N means that there are capital N number of coefficients, and capital N is even, therefore we require only n by 2 multipliers. We illustrate the structure with reference to two examples. Let's say capital N equal to 7. So in this case h of z is equal to h0 plus h1 z inverse. Note down, h0 is a short notation of h of 1, sorry, h of 0, and h1 is h of 1. Okay, don't get confused. Plus h2 z to the minus 2 plus h3 z to the minus 3 plus h4 z to the minus 4 plus h5 z to the minus 5 plus h6 z to the minus 6 plus h7 z to the minus 7. Am I correct? See, when I say n equal to 7 means there are 7 multipliers, but I have 8 multipliers, so let me delete these two guys. That's it. Then we can write this as follows. To draw the structure, it would be advisable to write the complete transfer function. That's why I have written it like this. And the symmetry point, where is it? This is the symmetry point. Okay, therefore h4 will be the same as h2, right? h5 will be the same as h1, and h6 will be the same as h0. So I can write h of z is equal to h0 plus h1 z inverse plus h2 z to the minus 2 plus h3 z to the minus 3, and this one I can write h0 is the same as h6. Therefore if you want, let me write down here h6 z to the minus 6 plus h5 z to the minus 5 plus h6 z to the minus 6. Now what you do, this h6 is the same as h0, therefore you can replace by h6 by h0 z to the minus 6 plus this one you replace by h1 z to the minus 5 plus this one you can replace by h2 z to the minus, am I writing correctly? I'm sorry, this is not h6. I'm very sorry. I beg your pardon. h4, h4 z to the minus 4. And what is h4? h4 is nothing but h2, so I can write h2. Now take this guy and this guy and then rearrange the equation, combine them, so you will get h0 within a bracket 1 plus z to the minus 6. Am I right? Let me check. Okay, and then correct. But okay, let's see. Plus h1 z inverse plus z to the minus 5 plus h2 z to the minus 2 plus z to the minus 4 plus h3 z to the minus 3. This is what you get after simplifying this. This h of z I can write y of z divided by x of z, and you take x of z to the right hand side. Okay, now let us draw the structure for this. The structure is little easy, so you can draw it very nicely. So what we do is we first draw all the delays. So how many delays do we need? 6 delays. So let me draw the 6 delays. First you draw 3 delays in this fashion in the top row. Z inverse like this, and then the other 3 delays in the reverse diagram. So this is in the forward path. Now you put the delay here, Z inverse, below this one more delay and one more delay, and this one goes like this, and that's it. So what you do is the undelayed term is now combined with the 6 delayed term. Look at here, this h0 is undelayed and again delayed by 6 times. So therefore if you take this x of z to the right hand side, you will get h0 1 plus z to the minus 6 times x of z. Therefore this x of z is multiplied by h naught. Okay, and first you add these two guys, and then you multiply by h naught, and this is what you will get. This point is h naught multiplied by 1 plus z to the minus 6 x of z, and this is a point, feeding point, x of z. So x of z comes here, and in this point you get x of z multiplied by z to the minus 6. So in this point you get x of z plus z to the minus 6 x of z. Therefore 1 plus z to the minus 6 times x of z, and then this quantity is multiplied by this guy, so you get this. That's it. So this one, and here you add these two guys, and then okay, so this point you get x of z multiplied by z inverse, and in this point you will get 1 2 3 4 5 delays, so z to the power minus 5 x of z. So add these two, x of z inverse plus x of z to the minus 5. If you take x of z commonly outside, then x of z multiply by z inverse plus z to the minus 5, and then what is the multiplier here? H1. So you put H1 here and then give it to the summer like this. Okay, so here also you first add this is a pickup node, and then this is multiplied by, what is a multiplier? H2. So H2, then give it to the summer. See, I interchangeably I use the notation plus sign and this sigma symbol. Nothing is wrong, you can use it. And then finally we add this guy. So H3 is multiplied by 3 delays. 1 delay, second delay and third delay. So this point is multiplied by H3, and then you put one more summer, and this is my final output. Okay, so in this point, if you look at H1 Z inverse plus H1 Z to the minus 5, and in the summer only 2 signals at a time is allowed. You cannot put more than 2 signals. So how many multipliers do we need here? 1, 2, 3 and 4. So we need 4 multipliers. What is the capital N value? Number of terms? 7. Therefore 7 plus 1 by 2, that is 4 multipliers we need. So it is canonic in delays. Canonic in delays. The structure is canonic in delays. So this is also an advantage of linear phase filters. So whenever you have linear phase filters, then it needs less number of hardware components, I mean less number of multipliers. And this is also an advantage of a linear phase. And not only that, they give constant group delay. So that is the main advantage we are going for this FIR filters. Linear phase FIR filter. Linear phase FIR filter gives constant group delays. And one more advantage is hardware requirement is lower. Now on the other hand, if capital N is equal to 8, let's say, the highest term is z to the minus 6. So in this case, h of z is equal to h0 plus h1 z inverse plus h2 z to the minus 2 plus h3 z to the minus 3 plus h4 z to the minus 4 plus h5 z to the minus 5 plus h6 z to the minus 6 plus h7 z to the minus 7. Now what is the condition for linear phase FIR filters? H of n is equal to h of capital N minus 1 minus small n. What is n here? 8. Therefore h of 8 minus 1, 7. So 7 minus n. So h of n is equal to 7 minus n. Substitute n equal to 0, then you'll get h0 is h7. So h0 is paired with the h7. Substitute n equal to 1, then h1 is paired with the h6. Substitute n equal to 2, then h2 is paired with the h5. Substitute n equal to 3, then these two guys are paired. That means what? h0 is the same as h7, h1 is the same as h6, then h2 is the same as h5, isn't it? And then h3 is the same as h4, and there is no loner terms. Therefore this expression can be written as h of z is equal to h0 plus h1 z inverse plus h2 z to the minus 2 plus h3 z to the minus 3. Now h4 is the same as h3. Therefore, instead of writing h4, let me write h3 z to the minus 4 plus h5 is the same as h2. Therefore, h2 z to the minus 5. And h1 is the same as h6. Therefore, h6 is replaced by h1 and z to the minus 6. Then h0 is the same as h7. Therefore, h7 z to the minus 7. Isn't it? So, if you simplify this, then this is not 7, this is 0. So h0 take commonly outside, 1 plus z to the minus 7 plus h1 z inverse plus z to the minus 6 plus h2 z to the minus 2 plus z to the minus 5, right, plus h3 z to the minus 3 plus z to the minus 4. This is h of z. H of z is y of z divided by x of z. So take x of z to the right hand side. Y of z is equal to h0 1 plus z to the minus 7 multiplied by x of z plus h1 z inverse plus z to the minus 6 times x of z plus h2 z to the minus 2 plus z to the minus 5 x of z plus h3 z to the minus 3 plus z to the minus 4 times x of z. This is my y of z. Now, as I said, what we do is we draw the delays in a different fashion. There are 7 delays. You draw 3 of them in the top row like this, and 3 more delays like this, and draw the extra one here like this, and this is x of z. You put the arrow mark, don't forget to put the arrow marks. I did wrongly here. Z inverse, Z inverse, Z inverse, Z inverse, Z inverse, Z inverse, Z inverse. Now what is the first term? First term is 1 plus z to the minus 6. So add these two guys and then multiply by h0. That's it. Okay, and then here h1 z inverse and z to the minus 6. This point is z inverse, so you put a summer here, and in this point z to the minus 6, 1 2 3 4 5 6, therefore z to the minus 6. Take these two guys, then output of this is multiplied by h1, and then you put a summer here and take output, and here also you put a summer, and this one is you multiply by h2 and then you put a summer, and you take this guy summer, and then this output you multiply by h3, you put a summer here. Okay, and this one is your final output. That's it. Okay, now we combine in the same manner as we did in the previous case, right? We combined this guy and this guy and multiply by h0. We combine this and multiplied by h1 and add all of them together. That's it. Okay, it shows not only the hardware structure, but also it shows the software structure. I mean, when I say software structure, it means that how to write the program. So the diagram, this diagram will indicate to you the successive steps in the algorithm, how to write the program in the software. And therefore this discipline is important. And you can find out the transpose also. Okay, so you can I already covered this, how to find the transpose. Interchange the input and output, first step, and the second step is reverse the arrow marks, and the third step is pickup node becomes the summer, and the fourth step is the summer becomes the pickup node, and do all those things in this diagram, and then you can find out the transpose. Okay, you can do that. It's a straightforward procedure. Okay, so what is the transpose of FIR, linear phase structures? That you can do it. So that's all about the implementation of linear phase FIR filter. So the important point to note down here is that it reduces the number of multipliers by half if n is even, and it reduces by n plus 1 by 2 if n is odd. That's it. So it reduces the number of multipliers. That is one advantage. So one should remember it. I think one more advantage also I have written. What is that? I forgot. Yeah, hardware, obviously yes, hardware requirement is lower because it needs a number of, less number of multipliers. So that's it. And one more, yeah, this is another advantage, constant group delay. So that is very, very important advantage. Because of that constant group delays only we are discussing FIR filters. Otherwise one will not discuss FIR filter. So the only reason we discuss FIR filter is that it gives constant group delay. So let us stop here. Thank you very much.